Good afternoon. Good. So today I would like to continue with the idea of the procedure of series summation and of the summation. And now today we learn how to tackle the typical physics problem, which is you have a power series that have the following properties. First, it has infinite number of terms. Second, it is a diverging series, asymptotic series in the sense that we define. And third, you can't calculate. You have no formula for general term of the series, and you must improvise with only 2-3 terms. So what should one do in such a case? We have seen two ways to accelerate the convergence of series. This was Shanks and what's it called? Richardson. We have seen two ways to regularize or to sum diverging series. This was the ideas of Borel and Euler. And now we would like to introduce to you and we also introduce the idea of continuous functions with the concept that continuous functions may allow one to actually make analytic continuation, right? Because we defined what we had last time. We had a function that was like sum over n of an x to the power of n, and we wrote it as e to b1, b0, e to the b1x, e to the b2x, And we have seen that in some cases, so first of all, we can derive one-to-one correspondence between the a's and the b's. And the good thing was that despite, in the example we gave, this series converges in a circle of radius, if I remember it correctly, 1 over e. But this approximant converges in a much larger region, right? So because both of them are identical inside the purple circle, I mean this is a plane of real x and imaginary x, because they are identical here, it implies that this continuation is unique, right? That's the idea of analytic continuation. And because of that, if we solve it, I mean, this is actually an extension of the function here, and this extension is unique. So we can say that this is the same; these are the same functions, and here it converges in a much wider region. Good. So, but okay, this continuous exponentials were just kind of a trick to an appetizer. The real thing we want to work with is continuous fractions. So what's a continuous fraction? We have again sum over from n equals 0 to infinity of say an x to the n. And we want to write it as b naught divided by 1 minus b1x divided by 1 minus b2x divided by 1 minus b3x, and so on and so forth. This is a continuous fraction. Do you know what happens when all the b's are 1?
You can say that it's equal to y, and then it's 1 over 1 minus y, and then you can calculate it.
Again?
You can say like all of these equal to y.
Okay, if all the x's are, all the b's are 1, right? Then I have 1 divided by 1. Maybe I have to, maybe all the 1 minus 1 over 1, no, these will be, maybe 1 over 1 plus b x. I think that this one, so all the b's are minus 1 except the first one. In that case, now you suggest me that since clearly this
is the same thing multiplied by
this
x.
is x times 1 times the same thing.
Yes.
Right? So it will get 1 over 1 plus xy is y.
Exactly.
Okay?
And then you can.
Well, y is a continuous thing, which implies that y y plus xy squared is equals to
1.
1. Okay? Y times xy squared is equals to 1. Now,
You can extract y from here.
now, okay, so what is y? So this is a, right, y squared plus y over x minus 1 equals 0. Okay?
Minus 1 over x.
Minus 1 over x, right. So, okay, let's assume that, so this is y as a function of x, right? Now, what's happened if x is 1?
Then 1 squared.
I have y squared plus y minus 1 is 0. So y will be minus 1 plus minus the square root of 1 plus 4. Right? So it's square root of 5.
פחות?
Hmm?
רואה אותו 5?
So yeah, 5.
5.
5, no, not pi.
5.
Right? Plus minus 1 over 2.
How did you get it?
This is square root of 5.
Okay, so it's minus 1 plus minus square root of 5.
Yes.
What?
The opposite.
It's minus 1 plus minus square root of 5.
Minus 1
Maybe 1 and minus, and then it's the golden ratio.
plus minus square root of 5. Yes.
Yes.
So minus of this is a golden mean. Right? And
I
that's
think if it was like from in this form, then it's exactly the golden ratio.
Hmm?
If it's in
Anyhow,
this form, it's
I mean, this is just
Yes,
a,
it's the
in this form is a golden mean?
it's I think
Okay.
because then you get
No.
no, then
No.
no.
Then I think it will diverge, because if I have, right, if I have something like minus, 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 and so on and so forth, then 1 over 1 minus xy will be equal to y, right? So y times y minus xy squared is 1.
Yes, it still doesn't the golden
So y squared minus y, if x is 1, then y squared minus y plus 1 is 0. No, I took it to the other side.
Yes, it still is the
Right?
golden
So now I have 1 plus minus square root of 1 of, sorry. Now it will be 1 minus 4.
Yes.
ratio. Yes.
Okay,
it's
so
still-
it's not going to be the golden mean. The golden mean is this one.
Yes.
Okay. Anyhow, this is continuous fraction, and these are examples to show you. Actually, I mean, why I am saying that I remember that there is a way to, you know, that each an irrational number is a number that cannot be written as m over n, where m and n are both integers, right? And of course, you can get as close as you want to any rational number by a rational approximation. And the golden mean is the most irrational number in the sense that you need, I mean, the way you approach an irrational number by rationals is by expressing it as a continuous fraction and cutting it whenever you like, be closer and closer to the rational thing. And the golden mean is the most irrational number in that sense.
Even more than transcendental numbers like pi and d?
Yes, yes. Golden mean is the most, because it's 1 plus 1 plus 1 plus 1, so there is no place where you can cut it and get good approximation. It's like there is no optimal truncation, so to speak.
Why would you want to approximate irrational numbers to a rational number?
What does it mean?
Why can't you just use an irrational number in some certain?
Well, if you want to write, I mean, to use it in a computer, then you must actually the computer is approximating it by rational. But there are many. Okay. If you have, for example, sine of irrational number times x, right? Or sine of some gamma, which is irrational number, times pi x, right? If it's rational, then this is a periodic function, right? And the more irrational it is, it will be almost, if it's irrational, it's not a periodic function, but it will be almost periodic. If you can approximate this gamma by m over n, right, it will be almost periodic in periods that make this after you can calculate, and if you take the golden mean, then it becomes as more maximally diverted from periodic function, if you like. Okay, but these are just mumbo jumbo about continuous fractions. The connection to the Hebrew calendar is for you to read. But what we like to do is to take a series and to express it as a continuous fraction. Right? So what we want to do is to make a connection between the A's and the B's. Right? For example, clearly A0 is simply B0. Right? Because if this is A0 plus A1x plus A2x squared. Right? What will be the up to x squared? So we can cut this one here, right? To get approximation up to x squared. And what we will get is B naught divided by, here I'm making a common denominator, so I have 1 minus B2 plus B1 x, and here I have 1 minus B2x. You see?
Shouldn't be minus. You did okay, never
I
mind.
took it upstairs. And now I will expand it. So I have B naught times 1 minus B2x times 1 plus B2 plus B1 x plus B2 plus B1 squared x squared. Right? Because I have to keep the x squared term here because there is a 1 here. Okay? So what I will get is B naught from this one and this one. And now I have from the 1 and this, I have minus x times B2 B0, right, from this. But I have also from this I have plus b naught b2 plus b1 x. You see? And now I have to keep the x squared terms. So the x squared terms will be this and that, and this and that. Right? So I'll have minus b2 times b2 plus b1 x squared. And I will have also, what else? I have this one.
B2 plus
right?
the B.
So what?
You forgot
B2 plus
B0.
minus.
This is minus.
Yeah, you forgot B0.
And b0, yes. And I have from this and that, I have plus b0 times b2 plus b1 squared x squared. So-
You forgot to put in this squared in B2 plus B1 should be squared.
No, this comes from here.
Oh.
This times that.
Yeah.
So all in all, we have b0.
Wait, what about the cube?
No, I am calculating only up to x squared.
Oh,
If I need x cubed, I have to include this term that I have thrown out. Okay? So I have b0, this is fine. I have here plus x, now I have b0 b2 plus b0 b1 minus b0 b2. So I have only b0 b1. And now I have plus x squared times this minus that. Now notice that I have both of them I have b0, right? Here I have b2 plus b1 squared, and here I have b2 plus b1 times b2. So I can write this as b2 plus b1 times b2 plus b. You see? And one of the b2 cancels, and I have b1 times b2 plus b1. Okay? And this will be a0, this will be a1, this will be a2, and so on and so forth. Notice that indeed, what is going on here, I am to calculate b0. If I know a0, I know b0, then I plug it here, and it's very easy to calculate b1 from a1, and then I plug it here, and it's very easy to calculate b2 given a2, b0, and b1. Every step I have to calculate only one number. It's not a complicated equation. Every step is very simple, right? You see? Now, of course, if you want it to third order, it becomes complicated. If you want it to 10th order, it's a real headache, but it is doable. Okay? Now, another feature of the continuous fraction, you can look at it in the following manner. You can say that a0 is b0, right? And I would like to claim, not I, the mathematicians like to say that this is a polynomial of degree 0 divided by a polynomial of degree 0. You agree? Now, a1 is this. Is b. Sorry. Okay. The first approximation is b0. The first approximation is b0, and b0 is a polynomial of degree 0 divided by a polynomial of degree 0. Now, the second approximation is this. This is a polynomial of degree 0 divided by a polynomial of degree 1. Now, the third approximation is b 1 minus b2x. Now, what it is now?
It is 1 in the
I mean, this is what we get here. So what we have here?
1 over 1.
We have a polynomial of degree 1 divided by a polynomial of degree 1. So the third one We have polynomial 0, polynomial 0, polynomial 0, polynomial 1. Now, okay. Now the third one is polynomial 1 divided by polynomial 1. Okay? What will happen if I will add here 1 minus b3x?
P2 over P1.
What?
P1 over P2.
Okay, the next one will be P1 over P2. And so on and so forth.
So it's 1 to the denominator, 1 to the
0,
denominator.
0, 1, 1, 0, 1, 1, 2, 2, 3, okay? The third one, the next one will be P2 over P2, and then we have P2 over P3, and so on. This is how it looks like. Okay? Now, this is, there is some choice here, because in general, we can forget about this specific form of continuous fraction and try to approximate, not to approximate, to write the sum of n of a n x to the n up to some like polynomial of degree n divided by polynomial, it's of degree q divided by polynomial of degree p. Okay? It's the other way around. I mean, this is just a common q. Now, how many free terms I have? Here I have, if I am taking it up to n, say, right? I will have a0 up to an, so I have n plus 1 constants. How many constants I have in a polynomial of degree p? What? P plus 1, because I have a0, so I have p plus 1 constants here, and here I have q plus 1. So all in all, I have p plus q plus 2, right? P plus q plus 2. However, we can always choose the first coefficient of the q. We can always choose to be 1. Right? So if we choose the first coefficient of the q to be 1, then we have p plus q plus 1, and we want p plus q plus 1, so p plus q must be equal to n. Right? And this is what you can see here. 0 plus 0 is 0, that's n equals 0. 0 plus 1 is 1, that's 1, 2, 3, and so on and so forth. But we can do that with many, I mean, we can decide to use, okay, so let me try to, what I'm trying to say is, this is P, this is Q, and we have zero, 1, 2, 3, 0, 1, 2, 3. In principle, we want P plus Q to be n, right? The way we are doing it by using the continuous fraction, in the way I show you, is to start from the 0, 0, then I go to the 0, 1, then I go to the 1, 1, 1, 2, 2, 2, and so on, right? We are going this way. Okay, this is a choice. This is called the main Pade sequence. Right? To do that. Okay? So our approximant, this is a technical term, approximant. The approximant to the sum of a n x to the n up to n, right, is the corresponding Pade, corresponding continuous function. Okay? Now, what this all is all about? What the hell? Why the hell we are interested in that? This is because of the following property, glorious point. This is the, I think, the worst black magic in physics. So, I mean, be prepared. Suppose I have a series, this series. Now, this series, suppose that this is diverging. I mean, I will be more specific in a moment. Some sort of asymptotic series, right? This is some sort of an asymptotic series, and you want to calculate the sum. You can't, of course. You have to do something because you can't add term by term because this will diverge. What I have taught you to do until now. What was my advice?
To find where it starts. Diverge, you start there.
Not where it starts. We say that every asymptotic series, if I'm calculating Sn, the nth term is something like that, and I have to find the minimum because this minimum is what, this was the idea of optimal truncation. In some cases, but if you are further away from the this is an asymptotic series as x goes to x0, but if you are further away from x0, you remember that it does like that, and you have no optimal truncation. Right? But this was the only advice that we have. Now we will give a much better advice. Suppose that the real answer is this. So this is the limit of the real limit, not the limit of the series, because the series have no limit, the diverging series. But the number we are interested in. Right? Suppose this is the number we are interested in. Then the sequence of PNN, what is PNN? It's 0, 0, 1, 1, 2, 2, 3, 3, and so on. The sequence of the PNN is doing something like that. And the sequence, this is n now, right? This is n. The sequence of P n, n plus 1, which is this one, this one, this one, and so on, is coming from here. Fantastic.
So remind me something.
Okay. Not only they converge, right? They give you also a upper and lower bound, right? Each time the next term will be closer to the right limit than the last term, right? They cannot do something like that. They cannot diverge. They cannot divert, right?
Even
This
though
is
the original series diverge? Even though the original series diverge?
Even though this, I will discuss the conditions in a moment, right? But this is what you want to do, right? So when you get you are doing perturbation theory, you get asymptotic series. You don't know what to do because if you just collect term by term by term, it diverges. Then one possibility is to try optimal truncation, but this implies that your preciseness is limited, right? You can't be more precise than something for each distance from the irregular singular point. But now you have no, I will discuss it in a minute, in principle you have no limitation on the preciseness, right? You can be as precise as you want, no matter if the series is doing like that or the series is doing like that. You just take the terms, plug them into the Padea approximant, and you will get them. This is, as I told you, it's a worst black magic in physics.
Where do you see a Padea sequence in nature? in nature, in physics, where do you see a Padek sequence?
You have to make, we will arrive at it, I guess, next lecture. You write, for example, Schrödinger equation with, you are doing perturbation theory with some small parameter, you get a sequence. This sequence, I mean, you get a series in epsilon, this series diverges. But if you plug it into the Padek, it get you the right answer.
It's weird that you take a diverging series and you force it to converge under.
Again, I'm repeating what I told you, I guess, last time. You have to. There is a function that describes something. For example, the ground state of a particle in some potential, right? For every potential that you write, there is such a number, right? And there is a function telling you you can write it as a function. So, for example, I'm jumping ahead to the next lecture, right? So suppose your Hamiltonian is p squared over 2m, which is p is the momentum, right? Plus 1/2 m omega squared x squared. Now this is a harmonic oscillator. And now you are adding something like epsilon x to the 4. Perturbation, right? Nobody knows how to solve this, how to find the eigenvalues of this, the eigenfunctions and the eigenvalues of this Hamiltonian. I mean, some people will tell you it's elliptic function, but saying elliptic function is like saying the answers for this Hamiltonian. I mean, you can always take something and call it, give it a name. Giving it a name is not okay. So the question is, what are the eigenvalues and the eigenfunctions of this Hamiltonian? For example, what will be the ground state? And you know that for the ground state is a function of epsilon, which for epsilon equals 0, it will be, I don't know, h bar omega over 2 or something, right? And for higher values of epsilon, you will have a correction of order epsilon and the correction of order epsilon squared and so on and so forth. So you get perturbation theory. Yes. So what you get is that the ground state energy is sum over n of some En, say En times epsilon to the power of n. This is a function of epsilon. You see what I'm saying?
Yes.
This is a function of epsilon. Now, if I am this function is, as I told you, the function is the holy thing in heaven, right? It's not. This is a revelation of the function, right?
Yeah.
And this is not a good revelation because you can sum it. Okay? But once you take this function and you write this series as a Padek sequence, right?
You can find
the
function.
It will converge very fast to the right answer.
So you can find E.
So this Padek is giving you another revelation of the function, which is more user-friendly. Okay? This is what's going on. This is essentially what is going on. And next lecture, I think we will, or I hope to arrive at it next lecture, we will explain it in detail. Yes?
How are we gonna find L?
What?
This letter L. It's like data from the experiment, or what? This is what.
Suppose you want, I mean, your ultimate goal as a physicist is to compare things with the experiment, right? So you have such an Hamiltonian, you know that epsilon is 0.1 in some whatever units, and now you measure the ground state, or you measure the ground state, you calculate the ground state, the first excited state, and then you know what will be the energy of a photon that jumps that correspond to this transition. You measure the energy of the photon very precisely, and you want to compare it with calculations of the ground state or of the first excited state.
when you teach, this is more how you teach in university. Why when you teach in universities, the presentation of functions, you teach them first as a summation of power. Of a Taylor Swift, and not like this, not like a
because this
sequence.
is, I mean, I'm repeating myself. If you are speaking about 1 plus x, yes, this is a function, and you write it as an right n(x to the n), this series converge only in the circle of radius 1, because this has a singularity at x equals -1. So the Taylor series converges only here. However, it is clear that 1 over 1 plus x is a perfectly nice function at x equals 3 or at x equals 1. No problem, it's 1/2, right? So this is a more friendly revelation of the function than this one,
Of course.
right? And Padé is yet another revelation that happens to be the right thing to use if you want to learn something about physics problems. Now, okay. Of course, all this is too good to be true. It cannot be the case that all the diverging series may be translated correctly in some sense to finite number using the Padé approximates, using a series of Padé approximates. So you may ask, of course you don't ask, but nevertheless I'm going to tell you, what are the conditions for the Padé approximation to work? Okay? And so, it turns out that, so you remember that it's a function, right? As I said, it's, for example, the ground set energy as a function of epsilon. It's a function of something, right? Which is our, okay, the x here, right? We want to calculate a function. So, so first of all, we would like to define, so the Padé trick is working for functions of Stieltjes. Okay, if this function is a function of Stieltjes, and it so happens that most of the physical problems that you treat perturbatively turn out to be functions of Stieltjes, right? If this function is a function of Stieltjes, then the Padé approximation works. The Padé approximant converge. So, okay, now you should ask me what? What the hell is a function of Stieltjes? Good. So here's the answer. A function of Stieltjes, I will write it as f of x, right? So f of x, like f is the ground set energy of the anharmonic oscillator, and epsilon is x, right? To see what I'm saying. So f of x is a function of Stieltjes if you can write it as the integral from 0 to infinity of some function of t divided by 1 plus xt dt. Okay, where two conditions. First of all, rho of t, which is called the weight function, rho of t is larger or equal to 0 when t is between 0 and infinity. So rho of t is positive semi-definite. That's right. You see what I'm saying? Okay? So this is condition number 1. And condition number 2, all moments exist. Meaning that the integral from 0 to infinity of t to the n times the weight function is smaller than infinity for all n.
This is the nth moment.
This is the nth moment of the weight function. Right? The nth moment of the weight function, and all the moments of the weight function exist. Meaning that, for example, every power law, every weight function, for example, if rho of t is e to the minus t, is that a function of Stieltjes?
It's gamma.
Yes.
Yes. Why?
It's gamma of n
has all the moments.
All the clearly all the moments exist,
And the soft
and
condition is also
the function is positive semi-definite. If rho of t is e to the minus t times sine of t, is that a function of Stiglitz?
no.
Why not?
Because the first condition.
The first condition is violated. If rho of t is 1 over 1 plus t to the power of 5, is that a function of Stiglitz?
The sixth moment doesn't-
No, because even the fifth moment, right? Even the fourth moment. But, okay, so you get the idea. So if a function is a function of Stiglitz, then Padé sequence converges. How do I show that? I have absolutely no idea. But somebody showed it. Either Padé or Stiglitz, I never understood who is. I think it was Stiglitz. Okay, now these are two conditions that make sure that the function is a function of Stiglitz. Now there is an alternative route if you want to show that a function is a function of Stiglitz, and you cannot write it in this form. You can still prove that it is a function of Stiglitz if it fulfills the following conditions. There are 4 conditions that allow you to, if they are fulfilled, then the function is a function of Stiglitz. What are these 4 conditions? A. If this is real x and this is image x, then for f of x to be a function of Stiglitz, it should be analytic in the cut plane. Analytic in the cut plane, meaning it's analytic everywhere except on the red line. This is condition number 1. Condition number 2, f of x is going to 0 as x goes to infinity. Right? By the way, notice that this function is satisfying these conditions. Because as x goes to infinity, it goes to 0. You see that? You can also see that it is analytic in the cut plane, because the only place where it is non-analytic is when x equals 0. Okay? Next, the third condition is that as x goes to 0, and goes to 0 I mean from everywhere, from here, from here, from here, from here. So maybe I should write it as f of z, but you see what I'm saying? X is a complex number. Maybe I will write it as z, right? If z goes to 0 as absolute value of z goes to infinity, no matter how. And when z goes to 0, then f of z is asymptotic to sum over from n equals 0 to infinity of -1 to the power of n times an times z to the power. And finally, for f, okay, I will show you. Look at this f, this integral, right? This integral, if I am writing it in the complex plane, so it's an integral from 0 to infinity of rho of t dt divided by 1 plus x plus iy times t, right? In the complex plane. Do you agree?
Yes.
Now I can write this thing as the integral from 0 to infinity of rho of t divided by, now let's multiply everything by the complex conjugate of this, right? So I have 1 plus x plus iy t times 1 plus x minus iy t. What's the answer?
1 plus t squared plus
1
y. 1 plus
Plus
xt squared.
x squared plus y squared t squared. You see? And then I have the mixed terms, but in the mixed terms the iy cancels out. And what I will have is
That's it.
2xt, I think. Right? And what I have here is 1 plus x minus iy t.
Are you sure you get a plus 2xt?
xt times 1 plus xt times 1. The minus the y cancel, so I will get it. This is the same equation, the same thing. Okay? So this is f of, say, x and y of z. This is f of z. Okay? Now, what is the imaginary part of f?
The minus I t.
Why I did that? I did that because now here you have something which is real, right? So I have the integral from 0 to infinity of rho of t divided by 1 plus x squared plus y squared t squared plus 2xy.
Times
And here I should keep only the minus I y t.
without the I, the imaginary.
The imaginary is without the I. Yes. Okay. Yeah. Okay. Fine. So this is the imaginary part. Note that this is wait. This is 2x times t. Right? Now, I would like to claim that this is positive definite function. Why is that? Rho of t is positive definite, right? This also is a positive definite function. Why? Can you show me why?
Well, x is greater than 0. T, the 1 plus x squared.
I
plus
can
y
write
squared is
it. I can write it as 1 plus xt squared plus y squared t squared. Do you agree? Right? 1 plus x squared t squared plus 2xt. Yes, so, and here you can see immediately that this is positive definite. So this is positive, right?
So
Now I will ask you what will be the sign of minus f of z.
F z is a complex number since when this.
Of minus, of the imaginary part of f of z.
Minus the sine of y.
minus the sum of
Minus
If I'm
the-
taking minus here, then this minus cancels out.
the sine
So-
of
So the sign will be the sign of y. So this implies that if I have this function, right, this is real z and this is the imaginary part of z, the minus of the imaginary part of f of z is positive here, right, and negative, so here it's positive, and here it's negative, and on this line is 0 because y is 0, right? You see, a function that admits this property, that it implies that the sign of the minus the imaginary part of f of z is simply the sign of
The conjugated f.
of the sign of
The conjugated.
the imaginary part of z. Right? If the imaginary part of z is positive, then the sign is positive. If it's negative, the sign is negative. And if the imaginary part of 0, then this is 0. Right? This property is called Herglotz.
On f of z or on minus f of z? Like, should it have the minus there for Herglotz, or like you say that minus?
It's positive when the imaginary part is positive, and
So you're talking about minus fz that is Herglotz.
minus imaginary part of f.
Okay.
This is
The
a
conjugated.
with the minus.
The conjugated f is positive.
Yeah. This is function is called either Herglotz or there's absolutely no chance that I spelled it correctly. Nevan. Ah. There are two guys, Herglotz and Nevanlina, that are responsible to this property. So every function that have these four, so now it's if and only if. Every function that has these four properties is a function of tildes, and every function of tildes has these four properties. And I showed you that the function of tildes has the Herglotz property. Okay? And you can very easily convince yourself that it has all the properties. Yes?
What is the reason for the minus 1 to the n? I can always tell that minus 1 to the n times a n is b. I can just say it's power series, right?
So an is larger than 0. Okay, you are correct. So it should be alternating
Yeah.
terms. Good. Now, so what? So for every function which is a function of tildes that satisfies either these two conditions or these four conditions that are completely equivalent, how to show that I have absolutely no idea. It's like, work of mathematical physicists in a paper of 500 pages. But if a function is a function of tildes, then what? Then the Padé main sequence, okay, I already erased it, but you know what Padé main sequence is. It's P0, 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 P1, Then the Padé main sequence converges. So both the P, the series of the P n plus 1 and the series of the P n n converge, one from above, one from below, and they not only they give you something, they converge, they also give you some upper and lower bound. These are the good news. Now comes the bad news. The bad news is that being a function of tildes, or be with whatever conditions you want, indeed guarantees that the Pnn and the Pnn plus 1, so the series of Pnn converges to a constant as n goes to infinity. It's not a diverging series like the original series, right? And the Pn plus 1 n also converging to a constant as n goes to infinity. The only problem is nobody proves yet. I mean, being a function of tildes is not a guarantee that these constants are the same. So it may happen that you will get something that converges to something here, and something that converge to another value here, and they will not converge to the right answer.
Does it happen, or like it shouldn't happen?
does.
But no one
It
knows?
does. It does.
So there's no reason to prove it if it's incorrect.
What?
You said no one proved that C1 is equal to C2. You can't prove it is if it's not necessarily true.
Wait. First of all, it's still a great improvement,
Yes.
right? Because you have taken serious the divergence, and you extract at least upper and lower bound. Thanks God.
Yeah, but the upper and lower bound doesn't necessarily convert to the answer you want. What
No,
do?
you have, but you have.
Yeah,
You
it's
can
it's
say that the ground state energy of your potential is between 1.234 and 1.236. In many cases, you don't need more than that.
Yeah,
you need much less than that.
It
But
is good that you
Yeah.
you have a.
okay, so now the question is, what are the cases in which you can show that the series that C1 equals C2, meaning that the two series converge to and then they must converge to the right answer. Well, under what conditions? Under what conditions C1 and C2 will be the same? Under what conditions you can prove it? Right? And the answer is that for this you have to apply to not else than Mr. Charlemagne. Known in Hebrew as Karel HaGadol, but it's not him that proves this, but a mathematician whose name was Charlemagne.
No, actually, Charlemagne.
This is what is written in the book. I copied it from.
No, not this guy. You meant Karel. Not Karel.
Karel HaGadol.
It's Charlemagne. It's another. It's
It's
not
a different word.
It's different word. It's not written
Yes.
like that. Yes.
That's weird.
It's
Okay.
actually written with a G somewhere. It's really weird.
Okay, I mean, I only remember that when I was walking in Frankfurt, I have seen a statue of a person, and it was written Karl der Gross, and it took me time to understand that the same guy. I mean, okay, so what is the Charlemagne condition? Charlemagne condition is that as n goes to infinity, an, what are the an? The an are the moments. You remember that we defined this is the moment. This is the nth moment, right? So an in absolute value, actually these an are always positive, are smaller than 2n factorial times c to the power of n. Okay? So we want the moment are allowed to grow, but not too fast. If they are growing slower than 2n factorial, then it's fine. If they are growing faster, then maybe the two series are converging, but not to the same number. Okay, this is the Charlemagne condition. Whether or not this is Karl the Great, I don't know. Okay, actually, it's a little bit, this condition is a little bit stronger than the actual condition. I mean, there is a weaker condition. The real condition is that the moment problem has a solution. You know what the moment problem? If they give you all the moment, can you retrieve the function? Right? You have all the moment of a function, all the moments of a function. Can you calculate the function? This is the moment problem. And the answer is that sometimes you can, sometimes you cannot. And this is a condition which is a little bit stronger than the actual condition. I mean, this condition also proves that the moment problem has a solution, but not the other way around. Okay? That's it. So
is that common for function to do all those 5 criteria?
Yeah, most of the perturbation theories in physics are satisfying are a function of Stieltjes, and at least the most famous ones are those who are satisfying the Charlemagne condition also. It's not a God-given property of physics, but close to it. One other thing that you can understand now is that you remember that what I told you is that here it is, right? It was here. That a function of Stieltjes is actually analytic in the complex plane, so it's all its divergences are concentrated here on the negative part of the real axis, right? And this is why the Padé approximation is so user-friendly. That's because these polynomis, right? You have polynomial like, I don't know, b0 times 1 minus b2x divided by 1 minus b1 plus b2x. This thing has non-analytic points, divergences. Where are the divergences? They are always on this line, on the real negative x. Okay? So the y, as I told you, I already told you that Taylor series is very poor because it must converge on a disk, right? And in order to do that, if the function is doing horrible things here, it affects what it does here. Okay? On the other hand, the Padé approximants allow you to throw all your troubles or your garbage to where it belongs, to the negative real axis, and then you get something that converges very nicely everywhere.
But here the divergence is on the positive real x, 1 over b1 plus b2.
Wait.
Maybe b1 and b2 are negative.
But
In this case, it's okay.
like, yes, but
Right. Okay, I have to think about this. Good. So far for series, okay? And what we have seen up to now in this lecture is that you can take a series from which you know only a few terms, and by implementing the Padé approximants, you get usually very good approximations to the quantity you are looking for, and we will extract these properties later on when we will discuss the the ground state, say, of an anharmonic oscillator. So this is a good point to end up the discussion of power series and start speaking about the next topic in our course, which is perturbation theory, right? So, as I already told you, did I tell you that perturbation theory is a justification of doing physics? I told you that.
I think you said it in the first lecture. or
Yeah,
something like
with Galileo and blah blah.
that. Yes,
Yes.
you did it.
Okay. So, what is perturbative expansion? So essentially, what we did until now was local analysis. The small parameter was the distance from x, the place where I want to evaluate the function. I have a function of x, right? And my small parameter, I want to evaluate it as x goes to x naught, and the small parameter was the distance x minus x. This was a small parameter for our analysis. Okay? Now let's speak about another small parameter, much closer to what we did in the first lecture. We have an equation, say y double prime is equals to some function of x times y, okay? And I have boundary conditions like y of 0 equals say 1, and let's do it with initial conditions. Y of 1 is 1, right? And I want to solve this equation. What does it mean? To integrate it forward in x. I know that it's y, I know the value of y and y prime, y prime of 0. I know the values of y and y prime at 0, and I want to know now what will be y at 1. But still I have to solve this equation. For example, if I put it f of x equal x, what I will get? 80. But maybe f of x is e to the sine x times ln x squared, right? It may be as horrible as I want. What should I do? So, what we are doing now, I will introduce an epsilon here, right? Now, here comes a very important set of rules that I will explain. I will write y of x as sum from n equals 0 to infinity of yn of x times epsilon to the power of n. You see? Now, I've taken one function that have initial conditions at 0, right? Now I have infinite number of functions. Okay, let's do that, right? We are writing that y0 double prime plus epsilon y prime double prime plus epsilon squared y2 double prime plus blah 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 is equal to epsilon times f of x times y0 plus y1 plus y2 blah 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 blah. Plus epsilon y1 plus epsilon squared y2 and so on and so forth. You see? You see what I'm doing?
Yes.
Okay. So now I will solve it epsilon to each order and epsilon in sequence. Right? So I will collect. What will be the first equation? To the power of epsilon to the power of 0. What will be the first equation?
y0 to jux is equal to epsilon fx y0.
y0 double prime is equal to?
Epsilon fx y0.
No, this contains an epsilon.
0.
0. Great. What will be the epsilon to the 1 equation?
y1 y prime equals fx y.
F of x times what?
y0.
Times y0. And since I solved y0 in the first step, this is just an inhomogeneous equation, which is very easily can be solved, right? And now what will be epsilon? The next set of equations?
y2 prime equals fx y1.
So it
And so on and so forth. So each time I'm solving for y, and then I will plug it here, and I will get always inhomogeneous linear equation.
So always you solve only for one y.
Yes.
Not
In
solving
each
for-
step, I'm solving only one equation. And then I will calculate all the y's, I plug them here, and I will sum the series. Okay.
Yes.
Next. Now here comes a problem, because let's start with this equation. What is the solution of this equation?
ax plus b.
y0 is a plus bx. How do I calculate a and b?
by initial conditions.
But wait,
You
the
can't
initial
do it.
conditions
for all
are
the-
for all the function, for all these guys. So how we divide sort of the initial conditions between, right? There is only one way to do that, and it's very important to remember it. The y0 of 0 is 1, y0 of y0 prime of 0 is 1, and for any other n not equals to 0, yn of 0 is yn prime of 0 is 0. So you put the boundary condition only in the first step,
The leading state.
in the leading step, and all the other steps have 0 boundary condition. First of all, you can see that this actually satisfies that, no matter what, right? If these are the boundary conditions, it always satisfies that, and there is no other way, because every
Depends
attempt
on
to
epsilon.
put different boundary conditions in different y's will give you something that depends on epsilon.
Why you assume that the actual things that you measure that in the boundaries is the leading order?
No. It may be many things, but to achieve a solution, you must work like that. So, what can I say about y? Given these boundary
1
conditions,
plus 1x.
what?
1 plus 1x.
1 plus x. You see? The function at 0 is 0, and its derivative at 0 is 0. Great. Next. Okay, so what is this equation? y1 double prime is what?
fx
Is f of x times 1 plus x.
and you should integrate.
And now, so what is y1?
Integral.
Double
Second
integral
integral.
from x to x.
Okay, y1 prime is an integral from 0 to x of f of t times 1 plus t dt. And y1 double prime,
No.
sorry, y1 is the integral from 0 to x dt, integral from 0 to t the
W.
s, say,
Works.
okay, let's call it dt, and this will be dt1 over f of t1 times 1 minus t1. 1 plus t. See? Good. So, and this satisfies, you can check that this satisfies the boundary conditions for the zeros, which is 0 at 0, and also the derivative is 0 at 0. This is, because of this fixes the lower bounds of these integrals. Because the equation by itself, the y double prime is that, fixes the upper bound, and the conditions for 0 fixes the fixing the lower bound. Okay. What will be y2?
Second integral.
Right? I should just replace
1 plus t1.
I should just replace what?
1 plus
t1.
t1.
I multiply. So I have f of x times this times y1, and I should, right? So what I will get is the integral from 0 to y2 is the integral from 0 to x dt integral from 0 to t dt1 over f of t1 times the integral from 0 to t1 dt2, the integral from 0 to t2 dt3 of f של t3 of t3 1 plus t t3. Wait, did I
Yes.
yes?
Yes. Yes.
Yes. Okay. Good. Now, and so on and so forth. Okay? Now, here is the question. Does this series converge?
Depends on epsilon.
Hmm?
It depends on epsilon.
On
Why?
epsilon, there isn't any epsilon dependency.
No, the series itself.
I think you meant the series like y's.
So, I will calculate this way all the y from 0 to infinity, and I will plug them here.
Ah.
Right? And the question is, does it converge? Very simple question. Okay. The answer, to get the answer, I will use the following argument. At the end of the day, I would like to calculate this integrals for t which is smaller than x. Right? See what I'm doing? I'm trying to calculate these integrals up to x. All the t's that are in the inner integrations are smaller than x. Right? You see what I'm saying? Now, I would like to claim that if I am taking this is 0 and this is x, right? And the function f of t must have a maximum between 0 and x, somewhere. Okay? So, a lower bound or an upper bound of, if I have an integral, for example, y1, right? y1, I would like to say is smaller than k times 1 minus plus x times the integral from 0 to x dt from 0 to t dt1 over nothing. You see why? Right? The integral is the area under this curve. Okay? Now I would like to replace it by the integral over this region. Because I replace everywhere f of something by the maximum value. So it must be the case that this is smaller than that. Okay? Now, what is this integral? What's the answer here?
X squared over 2.
Hmm?
X squared over 2.
This is, the first integral gives me t, and the integral over t dt is t squared over 2, so it's x squared over 2. So it's smaller than k times 1 plus x times x squared over 2. Now, what about the next term? What about y2? What is the upper bound now? You see that I have f, I have twice. Right? So y2 is smaller than k squared times 1 plus x times the integral 0x dt, 0t dt1, 0t1 dt2, 0t2 dt3. What is this? Monster?
No, you should have another 1 plus x.
No. No, I don't have another 1 plus x.
Oh.
There is only one 1 plus x.
Why is it 1 plus x and not x?
What?
Ah, it's
No.
There is,
Yeah.
right? The maximum of this thing is 1 plus x. Right? So I can take it out also.
Okay.
So I have it squared, and what is that?
X to the 4 over 24.
Of
Over 24.
over 24.
Over
Right?
oh, yeah, actually.
This will be k squared times 1 plus x times x
To the 4.
to the 4 divided by 24. By, let's see, this is t squared over 2, t cubed over 6, t to the 4 over 24. Yes. Okay. So I can say that the general term yn is maybe bounded by what? By k to the power of n. Sorry, it's yn. K to the power of n times 1 plus x times x to the 2n, right, over 2n factorial. And because of that, okay, this is yn, and now if I'm going back to the series that I wrote, the question is, does it converge? The answer is, yes, it converges for every x. Because what I have here is many things to the power of n, right? That gives me, in the worst case, exponential growth, right? I have sum y is a sum over, from n goes to 0 to infinity, of k epsilon x squared to the power of n. The epsilon is coming from the definition of the series. Times, I can put the 1 plus x outside.
It's not equal, it's less than.
What?
It's not equal,
It's less than.
Less than, sorry. Y is less than this divided by 2n factorial. And clearly, as n goes to infinity, the n factorial will win against this no matter what is that. Okay? So this series is converging for every what? Every x.
Wait, but this series, we know what this series should look like.
No, this is just a smaller equal. It's not. It's an upper bound of the series.
Yeah,
right.
but we know what the sum should converge.
Yes, but okay,
Really
but
matter.
fine. But this is no, because you have 2n factorial here. It's not an exponential. It's not an
You
exponential.
also have
You
x
can do
to
some
n.
mathematical tricks and
it's
get
a
to
vessel, I think.
exponential.
It's kind of a vessel.
You can do some mathematics tricks and get
זה
to
לא
an
כזה משנה,
exponential.
כי זה רק חסם עליון.
Yes, yes, of course. It doesn't matter. But okay, so what I want to make explicit now is that there was a way. I mean, if we were trying to do that by local analysis, by the method that we have described in the lectures until now, right? Then our strategy was as follows. If we were trying to do that by local analysis, right? Then the strategy was, I have y, I will write y as y naught plus y1x plus y2x squared and so on. y1, y2 are not okay, let's call it a. These are not functions. These are constants. And I will write f as f0 plus f1x plus f2x squared and so on. Again, the f's and the a's are not functions, are constants. Okay? And then I can write y double prime. So y double prime is 2a2. This goes away, this goes away. You see? Y double prime is 2a2 plus 6a3 plus blah 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 must be equal to f times y, which is, if I'm collecting terms, I have f0 a0
6a3x.
x, sorry, 6a3x plus, okay, plus 12 a4x squared and so on. And here I will have f0 a0 is not a coefficient of x, you see? And now plus f1 a0 plus a1 f0 x plus, you can continue it.
Shouldn't it be 24 a4?
I'm taking second derivative, 4 and 3.
Okay.
Okay? So it will tell me that A2 is F0, A0, A3 is F1, A0 plus A1, F0, and so on and so forth. Right? This is a local analysis version. Right? Now, this local analysis version will give me a series, but this series is analytic. This series is converging only in the radius of convergence of F. Right? Whereas this series, the perturbative expansion that we are doing, is converging everywhere. So this is the great advantage of the global analysis over the local analysis. In the local analysis, we have something that at most give us something that converges in the radius of convergence of the function, while in global analysis, we have gotten something that converges everywhere. Okay? So, this was our introduction to perturbation theory, global analysis. And of course, I didn't have time to talk about all what I plan to do, but what we are going to do in the next lecture, which is again very important, but I'm saying very important about everything. So I will. When I was a student here, there was a course in superconductivity. Somebody gave a course and he was a new immigrant from Russia, and he started by saying, okay, and the most important thing is what's called the effect? How do you call the effect? Meissner effect. The most important thing is the Meissner effect. Good. And then after 20 minutes, he said, the most important thing is London equation. And then after 20 minutes, he said, and the most important thing is quantization of flux, and so on and so forth. Until I realized he was using Hebrew, so he said, הדבר הכי חשוב. He didn't realize the difference between most important and very important. That's why he said, I mean, you can't say anything that anything is. But this here everything in all my courses it's like that. Everything is most important. So the most important thing that I will explain you next time is the distinction between singular and like the distinction that we made between singular points and regular points in the local analysis, the parallel in global analysis, in perturbation theory, is a distinction between between singular perturbations and regular perturbation theory. Where in regular perturbation theory, the answer when epsilon goes to 0, as epsilon becomes smaller and smaller, the answer is becoming closer and closer to the answer when epsilon is 0. Right? You see what I'm saying? Whereas in singular perturbation theory, it's definitely not the case. And there are a few very interesting and fascinating theories in physics in which you get confused because you have a small parameter, but if you take this parameter to be 0, you get completely different answer. And we will discuss it next time, right? That's what I told you. It's the apple in the maggot. I told you that, right? What's worse than finding a maggot in the apple? מה יותר גרוע מלמצוא תולעת בתפוח?
Finding half a maggot.
Finding half a maggot, right? Why?
Because it means you ate it.
It means you already ate half a maggot. Yeah, great. Now, what is worse than finding half a maggot in an apple?
Finding no maggot in an apple.
1/4.
Finding 1/4 of a maggot. Very nice. Why?
Because
Because this implies that you ate
more than
quarters of
half
the
a
maggot,
maggot.
right?
So the worst thing is to find any
okay, and now you can generalize this argument to say that to find 1 over n plus 1 of the maggot is worse than finding 1 over n of the maggot. But at the limit n goes to infinity, this is not the case anymore, right? Because now,
Finding no
if n
maggot
goes to infinity, you find no maggot in the apple, and finding no maggot in the apple is good.
It's the best thing you
The
can
best
find.
thing you can you
Let's
see.
say find a hole.
So
אתה לא יכול לדעת את זה.
מה?
But unless if you find a hole caused by a maggot, you can
Okay,
find the maggot,
now you are
then you
asking questions about a joke is prohibited by the 4th Geneva Treaty, and you shouldn't do that by under any circumstances. It's a war crime. So that's the point. I mean, that's the difference between singular and regular perturbation theory. In singular perturbation theory, when you take n goes to infinity, you get answer that is completely different than taking n to be as small as you want. So this will be next week.
This tutorial, his goal is practically giving you some intuition about the non-converging series. He already has some intuition from the lecture, but this is supposed to be more like you will ask question and I will answer. I have the tutorial notes, it's already published, but I'm not sure what Snell did with you or didn't, so you will need to tell me if I'm doing something that Snell did. But we will work through it, and if we will have some time, I can just open Bender's book and solve problems in live, so it's nice. Okay, we will start from Shanks transformation. Shanks transformation. By the way, this tutorial is really it's the application of what you will see here is mostly in QFT, so all you can be happy. That is a tutorial like you will probably not use it, but I don't know enough QFT to say
Field theory?
yes. Because in quantum field theory you often get to some divergent series that you need to sum, and you need to make some sort of an idea of what happened, and this is just how to do it appropriately. By the way, a nice thing that I'm not sure about is if you do Shanks transformation on divergent series, what really happened. I think from the example I will show you in 1 second, that it will give you the same result as Euler and Borel, but it will be much more quick, but I'm not sure, quicker. Okay, so Shanks transformation is basically taking the idea of you have an, okay, just a sequence of numbers, and in that numbers we have the limit, which we will call it and denote by a, and let's say it's actually, if we want to be exact, we will assume it is a of n, some function of n, plus some, let's call it lambda, don't remember how I call it in my lecture notes, let's call it by alpha times q to the n. Probably saw this in Schnell's lecture. And what I mean by an, why it's so important. What I'm doing here is pretty much say like, okay, an is going like some slowly variate function. It can be constant, it can be just n, and if it converge yay, let's say it's just slowly changing function, and the next term will be some exponential. We want it to be decaying. That is how Bender defined it. But what I told you before, that I'm pretty sure that will give you also a nice answer for divergence of something. So if n is a sum of let's say -1 to the n, it will actually give you, when you will do the Shanks transformation and all of those stuff, you will get half. So that is very nice. I'm pretty sure about it, you can check. So it's actually very nice. So what I'm saying is that is slowly changing, varies, and that is varies like an exponential. And the other terms we will pretty much neglect. If we will look on the converging case, so that means Q in absolute value is less than 1, what we get that, okay, something that is not included here, you know, with asymptotics, that way we have alpha, is converging faster than exponential, and therefore you can neglect it very quick. That is the intuition about it. And Shank's idea is say, okay, if that is slowly converging, what we can do? We are good physicists. I mean, that is pretty much constant, right? And that is not asymptotically goes like, that is exactly going like. We just remind you, we neglect all the terms which look like something like that. Let's call it like that. That is negligible, right? That very quick will be 0, and we just take the first term that converge. Okay, an equal to a. If you want, even for divergent series, if something is diverged faster than exponential, we don't care about its value. Borel and Euler will not tell you the value for that. And Shanks is pretty much working with Borel and Euler idea. Okay? And so you have an equal to that. You can write n minus 1 plus alpha q to the n minus 1. That you probably did with Snell, right?
Yes.
And then you got the Shanks transformation Sn of an, right? That thing. You just found the value of a, and that is the Shanks transformation. That is the main idea and what is behind that. I think from that presentation you can pretty much understand the idea behind all of it and why it will give you converging. And you get that is an plus 1, an minus 1. By the way, for continuous function, how it will go like? The numerator and denominator of Shanks transformation for continuous case. Okay, we'll just say the answer. What is that? The numerator is מכנה באנגלית. this part of the fraction is numerator term, right? Numerator and denominator, right? Okay. That is just if you have some function f of x, okay, and let's call that a of n. Let's call a n plus 1 to be f of x plus h, and a n minus 1 to be f of x minus h. When, well, okay, if you want to look on it, h is 1 approximately, or anything you can plug instead of x here, just n. What will happen if you will plug it into here is you will get that the numerator is just the second derivative of x times h squared. That is very cool. You know that probably from numerics course. And the denominator is f tag x squared times h squared. That is also very nice. Now you can have some feeling about how it will look like the Shanks transformation. If you will do just unit analysis, and you want, okay, you know that has the same units of a. But from that you can really see that very quick without just okay, dividing a and a. That will be f tag squared is like f squared divided by x squared. F2 tags is just f divided by x squared. You cancel things out and you get the same units of a. Okay. Why it's the same asymptotic? If that's not convincing you, we can probably do something with L'Hopital's rule and show that formally and rigorous that has the same limit. But we are physicians, it's a magician and physicist. We are physicians, so we don't care, we do just black magics. Okay, that is the idea. Let's do nice problem. Okay, we want to get the value of pi. What we can do, by the way, I will give you a horrible question on that if you want, on evaluating the value of pi. In the past they use Shanks transformation with some you know, not good values of function to evaluate pi to something like 10 million digits, decimal digits. So it's horrible. But this day we will do it with pi over 4, and you can guess with which function. Arctangents, arctan of 1, and we can use the fact that Taylor expansion of arctangents is just minus 1 to the n divided by 2n plus 1. By the way, I saw that exact problem in Bedner's book, but I were familiar to Shanks transformation by disuse of approximating pi, so I wrote that in LaTeX, the tutorial notes, and then when I start to look on problems for your homework, I saw it's also appearing there, so it's nice, but I'm the original. Okay, the YouTube video I saw is the original source, but for me, okay. So I will take the computer and we need to plug some to write some values, that is the right sum of it. Let's write it. Okay. Okay, we will note S by S the regular series and S at after doing the chunks transformation. Okay, so S1, what is it? S0, let's be
Just
1.
one.
S2,
1
you
minus
that you can do in your head.
1 minus 1 over
2/3. S3, that will be more hard to do in your head. That will be 2/3 plus 1/5. Okay, but I don't care about what it's really mean. I will just write it with decimals. Okay, S4. It will be, I will just tell you, 0.8359. S5, what it will be? 0.7456. Okay, but that is just numbers and using calculator. Can you infer from it what is the value of pi over 4? What it will be probably converged to? Okay, without plugging in 3.14.
0.8, 0.7.
Yeah, you can probably guess the first digit, but you're not able to guess the other digits. Okay, you know with each term it should be much more close, but how close it will be? We study in numerics, and we study it, I think I mentioned it in one of the tutorials.
Like the reminder of.
Yeah, the reminder, the next term in the Taylor series. Yeah, now I remember when I talked about truncating some divergent series in a symptotic series, when do you know where to stop? We talked about the reminder is just equal to, it's bounded by the next term. Okay. Right. So that thing, you can guess 0.7 because I see here I have 0.6 and 0.8. I will do average because I'm a physician, and I will get 0.7. I can guess. I can look on that and.
You said physician. Physician is a doctor. It's someone in medicine.
Yeah, but when I'm saying physician, I mean physics plus physicist plus magician together is physician. Because today we will be physicians, not
I don't
physicists.
think this is how English works.
It works like in this tutorial, okay?
Okay.
We already do some magic series, so that is another magic. Okay. So 0.7 is probably a nice guess, but what will be nice to do? Look on chunks transformation for S3. I want to convince you that chunks transformation will converge very quick. And the value for S3 is, I calculated it, 0.78188820. Okay? Remember that for calculating S3 we needed S4, right? So
why don't you simply use shanks on shanks?
Why can't I use? I can use. and you have some examples in Bender's book that you will see actually it will get better.
Yeah.
But what is
If you
bad
add
when you're
shanks
doing
If you add shanks for 1 and shanks for 2, you can use shanks on shanks and find a better.
You want to do it infinitely many times and think that will work, but the point is each time you use shanks you need more terms for the original series, right? If you do it infinitely many times you need infinite terms from the original series. If you have infinite terms from the original series you already have the limit, so why bothering you with calculations? It's something like the conservation of hardness of problems, but okay. So you probably wonder what is pi over 4, right? And can someone guess? Pi over 4 is actually 0.78. Let's see. Where you wrote it? 0.853982. Okay, what is closer? S4 or S3?
It's free of the shank.
Yeah, and you can see S4 is right for only one decimal number. S3 is right for 1, 2, and the missing in the third number. As you will progress in chunks, you will get much better than the original series because you have more information. So, like you said, you can just use again and again and again the chunks transformation, and you will get something that.
If you use chunks.
Wait. So you can get better and better and close to the limit. The a little bit weak point of chunks transformation is it's very sensitive for constants. What do we mean by constants? If I'm constant, if I have a series that is it's converging to a number but in 3 terms, something like that. I have a series, it's converged to some limit that is y equal L. What happened here? I have 3 terms that equal to each other. When I will get to that term, the numerator will be 0 and we will get just a peak of infinite, and that is not bad, that is very bad. So the problem is if it's I will give you some rule. If it's something that is spiky or have some weird convergence like spikes or something like that, it can be bad. It pretty much assumes you have something that is very smooth and continuous. So that is the bad part. But when you're doing theory, you are pretty much searching for something that's smooth, and physicians, so everything is smooth. So for our case, it's nice. Mathematicians will say that is very bad, that not work for all series. Only series that you can continue analytically to, there is analytical function for smooth function that pass for all points. Okay, your question.
I didn't have a question.
You start to say something.
No, I didn't
Okay.
have it.
So there is not more questions. I will continue. Most of the problem in that area is basically the first course you had in math in university. it's something like, okay, taking the limit of that you already know, and if you don't know, just go through it again, read on it, and recall what is it. I think there are better stuff to do. If you want, I can do it in the end of the tutorial if we will have time. But that's pretty much, okay, how do you prove that is converging to a limit, or what is the limit of Shanks transformation of that series? That to determine the limit of the original series is very complicated, but Shanks pretty much simplify everything. That is not very interesting, in my opinion. Okay, that is interesting, but for our case, there are better stuff to do. Now we will do Richardson extrapolation. Did I miss something in Shanks that Snurb said or did? And
he mentioned that you can shanks the shanks. You can take
yes, I mentioned it already that we can take more terms and continue with that. If I will give you n terms,
No,
you
I
can
mean that if you have like
you can do Shanks transformation n
No,
times
okay.
and get.
No, I mean
No,
that
what-
if you have like S3 of shanks and S4 of shanks and then 5 of shanks, you can do shanks of the shanks. You can do shanks transformation for the shanks transformation.
Yes,
You know?
that's what I meant here. If you have n terms, you can do n Shanks transformation, and that is how you will get more and more
Yeah,
numbers.
He said it's like an accelerator.
Yeah, it's accelerating very, very quick. And don't remember, there is a problem in Bender's book, which I consider to give you to calculate how better it gets, but then I realized, okay, we are physicists, we don't care how better it gets better. We know that mathematicians prove how better it gets from each time we apply Shanks transformation, and there are more applicatable, nice problems that it can give you that worth your time. So I didn't give that in homework. Maybe as a bonus
Everything
we
on
give
this
that,
course
but
is
I
from
don't
the-
think that is worth it.
Everything on this course is from the Bender book? Is
Yes,
the book from
everything.
Bender?
Okay. Richardson method. Okay. That is pretty much if you want to find the convergence, let's say, of a series that you want to sum. Okay? Let's give the example of zeta of 1.1. That is not written in my tutorial notes, but I will give you that example. You know what is the zeta function?
Yes.
What is the zeta function? What is zeta of s?
Sum over the sum of 1 over n to the power
1 over n and to the s. Right. And I heard from Snurb that you already heard about Riemann hypothesis. Hypothesis, I don't know how to pronounce that. Okay. So you're familiar with that function. In the past, they tried to calculate for some rational number the value of zeta. And just in order to give your some intuition how bad just taking the original series is, to get something they feel, okay, we have the intuition what is the number zeta of 1.1, they had to take 10 to the 20 numbers. You can pretty much calculate it with some calculus stuff, and if you want I can show to you after the tutorial, but there is no need to. You can just take in some approximations, and to get something like 100 numbers,
You mean this is value of
100 numbers beyond the decimal point, that is how much digits,
How much
I'm sorry, terms you need to take and sum. that is very bad. We want nice stuff, nothing that will be nice. By the way, why 1.1 given you the problem? Because it's so close to divergent, right? If S will be 1, it will diverge. If S is slightly bigger than 1, it's converge. So, yeah, slow. If you want a better way to approximate things that close to 1 is do 1 plus delta and take a couple terms of Taylor and do ln and calculate the ln. So that will be probably much better if you want to calculate. But there is a problem. Numerically, there is a problem with calculating some series that are close to diverge. That when Richardson extrapolation comes to be handy, is basically saying something like that. If you have a sequence of number, it can be the sum from A0 to AN, or it can be just general. You can, okay, every sum is also a sequence of a series of number, right? Why? And vice versa. Why? Because you have telescopic series. You can write all sums AN with AN minus AN minus 1 plus AN minus 1 what? Minus AN minus 2 plus ta 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 A1 minus A0 plus, let's say we need to cancel A0, so we say that the first term is A0 also, the zeroth term if you want to, and not A0, it will be the minus 1 term will be 0. Okay, and in that way you can look, hey, there is a sum, and the limit of that is basically the limit of that telescopic series. Summation, okay, never mind. And you can look on the partial sums to n of some arbitrary series, and that is a series. So they are practically the same. Everything that you prove on AN you can apply to SN and vice versa. So you can prove it on one and say how it applies to the other one. It will be the same. Okay. So what we're saying is AN is approximately goes like Q0 plus Q1 divided by N plus Q2 divided by N2, something like that. If you need to prove that, right, in order to use Richardson extrapolation, because it can go like something with exponentials, e to the minus n, e to the minus 2n, and with that you can progress. But that will not be Richardson extrapolation. Richardson extrapolation is for that. You can apply the same for other cases, but you need to make sure what happened here. Okay, and he's pretty much saying, okay, now AN, you can calculate it. You have a computer, you are strong, you can do everything. Now what you want to do is find Q0. if it's going like that. So what you're doing is writing, okay, we're a physicist, that's equal, and now we are writing n plus 1 with q0 plus q1 n plus 1 plus ta 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 ta. Then we're continuing to how much, as long as you will continue, you will need to find more terms in the asymptotics. It can be a pain in the butt to do that, but okay, let's assume we found n terms. We get, let's say, n plus n plus ta 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 ta. Okay, and from here you just cut it at qn, right? Are you with me? You can cut it at qn divided n to the n, and now you have a linear equation that you want to find q0, and from that you can find q0. Right? Everyone understand? I wrote a nice matrix of the linear equation, and Snell probably showed you the general solution for q0. You saw that? Okay, so I will write it. Okay, so if you saw that in Snell's lecture, I will not do that. But what I will do is, you didn't do k squared divide 1 over k squared sum.
We did. Pi squared over 6.
Yes, you did that with Richardson?
Yes.
Okay, took what I want to do. You saw how to get the asymptotics of that.
Yes.
Oh my God.
To destroy Richardson.
Yes, I want to do the exact same thing. Because it's nice stuff that I want to do with the integral. You did that.
Don't think we did an integral.
You proved it. Okay, and the hard part is prove that an is going like that. That you did
For what example?
for zeta of 2.
Yes.
It's pretty much 1 over
N squared.
n squared. You did that?
Mhm.
You proved that with the integral?
I don't think so. I don't remember, so maybe we did.
Okay, I will do it soon. But stop me if you already did. I tried to catch within a talk for something like a week. But okay. The thing you're pretty much doing is, okay, that you want to be equal to that you know already. You don't know the value. Okay, so most of those proofs of sums is pretty much like that. Just saying, okay, that is q0. Sometimes, like in our case, we know the exact value of q0, but in other case, you're not always know. You don't always know that. And then you just take that thing and square and write that in integral form, which you can prove that that is the same thing. Let's see, t e to the t minus 1 times e to the minus n t, I think. N need to be capital. What did they do here? Yes, that is capital N. You can prove that very easily. I will not do that. I can do that, but that is just calculations. If you want, I can show you afterwards. But that is basically you taking Taylor series and you're done. And some definition of gamma function and all of those stuff. So you get it like that, and from here, you know, actually, now you did some manipulations on the function to reach here, and you use the other Taylor series to get to that form. But now, what you're saying is you know the Taylor series from that, for that. That is just, we did with Ruchman, Math of Physicist 3. I know you didn't, but you are.
I did, but I don't remember.
That is just the generating function for Bernoulli numbers. B2n x to the, okay, now it's t to the 2n, and then using the gamma function you can just show that. That is the interesting part. The other part, which you probably saw with Snell and he gave you the values, that is not interesting. That is the art of it, which I'm interested in because that you already know from undergrad studies. That is not interesting. If you want, I can give you another example of it, but it's pretty much every time you need to or do something like that, find some integral representation of the sum, or do something very nice in other methods, but I'm not sure which more methods you have. Each time it varies. Okay. Actually, prepared another nice stuff on Richardson. That is just an anecdote, but this time it will be much easier to prove. Where is it? That assumption, but it will be much cooler result. Oz, what is your favorite function?
The best function.
Right. So now we will use Richardson in order to approximate the Bessel function. Wait a second. We defined a sequence. Like I told you, sequence is the same as summation series and all of those stuff. Actually, a summation series is a little bit complicated, which defined by this recursion, and we define the boundaries of. You need to define a minus 1, I think it's 0, and a minus 2 is 1. You can get that recursion from just using Bessel differential equation. That is very easy. If you want, you can do it later. And for me, from using that, you actually get that the limit of an when n goes to infinity is I0 of 2x. That is from the recursion. You get that from Bessel equation. What I want to present here is basically you found that recursion that is for given x. You want to calculate that for given x. You can't calculate that analytically otherwise. You're doing, it's pretty much numeric method. Okay. For given x, we want to calculate I0 of 2x. So if you want to, I0 of x is just divided by 4, you will get that. Why, Dima?
Okay.
Okay. Yes. So that is pretty much the solution to that. And now, just using Richardson, what we need to do is to prove that, how that goes like. But you can see from here, you can just taking the telescopic series, you can prove by, okay, what is 1 over n plus 1? It is just 1 over n minus 1 over n plus 1. And they're pretty much the same, I know, but you can say, okay, it's pretty much taking the derivative, so it approximately goes like 1 over n squared. And then by induction of an is approximately looking like that, you can prove that on A0. Okay, easy. Now assume it on n and prove it for n plus 1. But okay, we have that relation. That goes like that, that goes like that, and the sum of two things that look like that is the same. I'm not saying that the constants is the same, but they will be approached to be the same. Why? Okay, that I didn't prove, but you can see intuitively why it's like that. I think that is good enough for our course. Mathematician will argue if that proof, but that is good enough. Today we are physicians. It's magician and physicist. You were not here, but I said that in the start of the tutorial. Now we're going to start some black magic, which in my opinion is much more interesting. By the way, you got a mail that we have a tutorial on Sunday 10 in the morning. Okay, so Dima, remind me to send a mail. Not tomorrow, Sunday. Say it Sunday? Okay. So now we will talk about Euler summation. But basically I want to present here, I don't think Snell presented the formal way of thinking about it. I think it's organized in the mind of how you should look on that stuff. He probably showed you, okay, if I have a machine that's summing divergent series, I assume something that is wrong, that this divergent series is converging, what do you get? What I will try to do is explain to you why you can adjust a unique value to that. I think, in my opinion, when I see it with someone that presents it like a machine, I'm like, okay, but if I want the value to be 2, I can probably get in that way too also, because 1 minus 1 plus 1 minus 1 plus 1 minus 1 it looks to me like 0, because you can sum it with waving hands. But as I told you in the start of the tutorial, I have infinite number of zeros. Usually, infinite number of zeros is 0. In our case, for a divergent series, because its original form were minus 1 over n, so it is not the same, and it's not 0, the sum of zeros. So you can do some of the stuff. So what you did with Schnell, mathematician will argue with that, but I will present you the formal way, and that will leading us to Euler and Borel. And then I have a nice stuff that it's taking from inspiration from Feynman diagram. Nimrod and Oz can smile. And then we will go on. We will finish. Okay, so the basic idea in Euler summation. The basic idea of that. The basic idea of that is, okay, if I have a function, if I have a sum a(n) which I want to determine. By the way, with what I told you already of summation and series, how that called? What I told you on summation and limits, that they are the same. Everything that I'm saying on sums, just need to take the telescopic summation of a series, and you get equivalent form of for series, right? So you can define Euler summation for series, and then you get a limit that is finite for divergent series. That is sequence, right? Exactly. Okay, so if you have a(n) which diverge, okay, the basic idea of Euler, so like, okay, you know the thing that happens sometimes in calculus when you are outside, when you are on the boundary of the convergence, that you have minus r, Nimrod, if you want to talk outside, please. Feel here, so don't need to try. Okay. Minus r and r, but there is no formula for determining if it's converged on the boundaries. There is not general rule, you just need to plug in and check. Right? For ln x plus 1, you need to check. For 0, it's not, for ln of 0, if you want to plug in minus 1, you'll get nothing, but if you will plug 1, because the radius of convergence is 1, you will get ln 2 in the Leibniz formula, right? But in our case, we know there is no rule. Pretty much what Euler said, okay, what if, he said, okay, if that diverge, but maybe that comes from someone that did calculus wrong and took the limit to the radius of convergence inside and switched that. Maybe that series came from that, so you want to do the opposite to get the steps back, take steps back, and then do calculus properly. Find what the sum is, and then find what's the limit. So what he said is like, okay, if I have the sum a(n) x to the n, now I can write it as a function f of x, and maybe the function f of x, which that is the Taylor representation of it, which is unique. Yeah, it's unique in the region. In our case, it's bounded by -1 and 1. Why? The radius of convergence can be larger than 1 because you have, for x equal 1, you have diverged. So it should be a subset of minus 1, 1. And what I'm saying is, okay, if you can take that sum and f is defined outside, you get a value for that. That will be f of 1. That will be our value. And why it's unique? Because if there is a function that agrees on the same values for even the smallest neighborhood, right? That is the word for that. A, comma, B. From how that's called, complex analysis, we know if they are agreeing even on a countable set, which we can define convergence of two functions, and the functions are the same on all points, those functions are the same. So for a neighborhood, you can define a series that will converge, right? And you can define everything you want pretty much, and all functions that agree on a neighborhood, like I told you inside the radius of convergence, you get the uniqueness. That's why there is no the only magic here is pretty much complex analysis, which is I don't want to say that in the record, but brain fucking. You know, it's if you can take the derivative once, you can take it infinitely many times. That is one of the theorems from complex analysis. That is pretty amazing, if you ask me. So that is the idea of Euler. Let's do some examples. You will tell me if you did them or not. I show that, and let's start from something. You show that 1 plus 0 plus 0 plus 0 plus 0 plus minus 1 plus 0 plus 0 plus 1 plus with k zeros, let's say k minus 1 zeros, is equal to half.
We show that for 3 zeros, but yes.
For 3 zeros.
Really?
Generalizing
Yes, yes.
generalizing is very easy. You have that sequence of numbers. What is the representation, Euler representation of it? Let's call that x. Will be just minus x to the k to the n, summing of all n from n equals 0 to infinity, right? Each time, I'm sorry, that is just geometric series. Then you get 1 over x to the k, which is our f of x. And by taking x to 1 on that function, we get that is half. So actually, adding equal amount of zeros in the in that series on minus 1 to the n is not affecting the series. By the way, I'm not sure, but if you will do something like that, 1 plus minus 1 plus 0 plus 1 plus 0 plus 0 plus minus 1, each time I'm increasing the number of zeros by 1, I'm not sure what will happen. You can very easily represent that with summing from n equals 0 to infinity of minus x to the n plus 1 divided by 2. I'm not sure what will happen if you will be able to find the f of x and substitute 1. Not sure what will happen, but I'm pretty sure that will converge to something. I'm not sure how to do that. If someone knows, I will give them 100 in the homeworks. Okay? In that specific homework that we upload today. I'm not sure, but it's interesting because I don't know if that allowed to add zeros as we want in that case. And I think because the number of zeros are increasing and increasing and increasing, and you can say, not formally, that most of those numbers in that sequence will be zeros, I think that will be 0, in my opinion, but I'm not sure at all. If you want to look on that as like taking average of some sort, you do measure theory, so maybe it will mean more to you.
אתה מניח שאני נכנס להרצאות של בוריס.
Okay, I don't know. I'm not. I will not tell you to go to lectures, but you should go.
כאילו
to
אחד עם קבוצה מידה 0?
Yes, the terms that are not zeros, if you want to look on the size of them, how many there are, and maybe defining a probability, all probability will tell you in probability 1, you will choose a 0 in that sequence, so that will be 0, in my opinion, but I'm not sure how to do it rigorous. So if someone knows, please do that and send me. I don't think and you saw why sum over n x to the n is not defined. Okay, so let's look on a case that Euler is not working, and let's from that find a nice solution. We'll give you also an intuition for that at the end, why it's not working here. Okay. I mean by summing all of those
okay,
stuff.
we did it. I thought
We did that.
No,
You
we
did
did
that
also
with
with,
Euler
You can say
summation?
that it's the derivative of x to the n.
we did it with Snell also. I thought you were writing n to the power of x to the power of. Couldn't understand. the
Okay,
You can say that it's the derivative of x to the n.
of x to the n.
Take the
Okay,
sum.
I understand that, but that Euler method will not work here. You
I
did
can-
that with Schnell, I saw
You can
already,
divide
Dima
the
showed me,
term by term.
but you did that not formally, right? That we're not formally.
You mean that we can divide term by term in here because it's not absolutely convergent? Uniformly convergent?
Okay?
אי אפשר לעשות זה כי זה לא מתכנס במידה שווה? אז אני לא יכול לגזור איבר איבר?
No, we are doing black magic. It's okay, you can do anything you want pretty much,
אז
but
למה זה לא עובד?
okay, I will show you. Because the radius of convergence not letting us do that. What I start to explain, that will be x to the x minus 1 squared. So that is our f of x. But taking the limit of x to 1 with from the negative side of f of x will be infinity, which is undefined by Euler method.
שנרב הרענו, אבל זה את הפונקשן רגוליישן, ואז זה מינוס חלקי 12.
Yeah, you can do it with zeta function. It's working. I know a proof of that from doing the analytical extension of zeta function. It's pretty much the same. And okay, you can do that with zeta function. I agree. But what I'm saying here, that will not work. That is the point. From Euler method, it's not working. And by the way, you can try one thing that will actually work, will be n times minus x to the n. Now it will work. Why? Because that will be x divided by x plus 1 to the power of 2. And if you will plug x equal to 1 on that, you will get 1/4.
אבל זה 1 פחות 2 ועוד 3.
What is the problem? Oh, you say it's minus.
No, it's 1 minus 2 plus 3 minus 4. It's not 1 plus 2 plus 3 plus 4.
Here it's 1, yes. I didn't say that is equivalent. I say it's different case. Euler series can work on that. What we will see is the intuition for me when Euler will work on or will not work is pretty much think about that as energies, and you in Euler method you can't sum something that will not alternate. That is my intuition. What?
דרך לסם.
Okay. I'm not, as a physician, I'm not familiar with your words. So I said magician and physicist. So it's pretty much when you're adding terms, if they are not alternating, you will not get answer from Euler method. Most of the time. Okay. So let's continue to Borel method. Borel is pretty much saying the same. The formalistic is the same, but he defined a function b of x, integral from 0 to infinity, of what? E to the minus t times phi of xt. Do you know what is generating a sequence function? Okay, we pretty much did that in the first tutorial. Generating function is a function that the nth derivative is the nth number in the sequence. So phi of t, if an is our sequence, it's an divided by n factorial t to the n. The nth derivative of phi at 0 will be an, that's called generating function. So it's not so random that Borel thought about that function and knew about that trick. Okay, you see there is a gamma function that, not formally, but plugging in that, you can look that t to the n e to the minus t will give you n factorial, and then you will get Euler sum, and if you will plug 1 you will get what we want. So it's just generalization of the idea of Euler, which Borel were familiar with generating function and then just find it. How do you find generating function if you have some strange looking function?
Just integrate for each part.
Okay, it's working. What? No, you can't do that because you can plug in. The idea is if you will plug in and switch the integral and the summation, you will get divergent series. So in our case, you can't do that if you want to find that. You actually need to find phi. How do you do that? You have a couple of options. The first one, which we didn't cover by now, is Laplace method, which Laplace method is pretty much saying that I will tell you in words, but you don't need to worry about that right now. Pretty much saying that what contributes to that sum is, for given t, the n that will give you the maximal number. And then you do perturbation on n plus small k and integrate from k minus infinity to infinity. When k is very small and you do a lot of Taylor series and very nasty stuff, and then you get approximately the function. Never mind. For now it's not. When we will talk about integration method, we will cover that also. That is some summation method. But for now, what we can do is what we did in the first tutorial. How do you find that? If that is generating function, one of the nice thing you can do, you have a of n, and if it comes from recursion, you can take derivatives. And like we did in the first tutorial, you can get back to the first tutorial to find the generating function of Fibonacci number. You can do it also here. That is nice. We can use that actually, I think, to find, okay, maybe we will do that. I don't know why I didn't thought about that, but I will give you that in homework. It's good. Of the sum of minus 1 to the n f of n. It's very nice.
The Fibonacci sequence, right?
Yes, that is Fibonacci sequence. That is nice. I will add that to the homework instead of one nasty problem, so that is good. And you know already what is phi for that case, because we find that in the first tutorial. Wow, it's really hot here. It's the temperature of hell. Okay, so I have some nice examples that probably Snirv did. Did he do the generalization of Borel summation?
I don't remember.
Okay, we have time for that. I have a lot of time, so. What I'm trying to say is, Borel also generalized this idea. He said, okay, if I can do that once, divide by n factorial and take in the sum, I can do that as many times as I want. The only thing, okay, let's assume that now we have some generalized. Now we didn't look on phi as a generating function, but instead he looked on that, okay, you can divide by n factorial, like the obvious perspective of that. You first look on that as a generating function, like I told you. We will call that kth order phi, and that will be an n factorial to the k x to the n. And the idea here that you will define now the Borel function with k integral. So I'm a mathematician, so I will write it like a mathematician because I'm lazy. Okay. We have minus t1 plus ta 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 plus tk, right? And then you have here x times the product to k of ti from I equal to 1. Inside the phi, you can see why, because separating will be possible here after taking the sum out. And then we have, let's denote that like in statistical mechanics notation, capital T, and then writing it with K. And then we got the summation. So we can generalize the idea and do whatever we want. And V of 1 is our sum, right? So that is nice. And now we can do some nice example. Let's do a basic example of that, of minus 1 to the n factorial squared. We can just do the same thing that we did here now. Let's look on phi 2 of x. What it will be? 1 over x, because it will be now a geometric series of minus x to the n. Do you see that? Or I will do it slowly.
I don't.
Okay. You gave me the face of I don't see that, so we will do it slowly. N factorial squared by definition. Now plugging in, that is our an, right? Minus 1 to the n factorial squared x to the n. Now we get minus x to the n because that cancels with that. And then we find that is 1 over 1 plus x. And that is how we can practically define some more generalized method of taking the value of divergent series. But it's still alternating sums. You see why applying our method as many times as you want to the sum of n, it will not work in our case because it's not alternating. In physics it's actually useful, but you will see in a second why. Because mostly perturbations, taking x perturbation you get a little bit higher than what you were supposed to get, and then taking next perturbation and you're a little bit lower, and then taking the next perturbation and you're converging with something like that when you're doing perturbation theory like in quantum mechanics too. Most of the time you have minus 1 to the n. So it worked for that case, and I think if you will do quality oscillator, I try to do that, and the quality oscillator is just adding to harmonic oscillator some lambda x to the 4. The kth perturbation will go something like constant times lambda to the k, that we know that is the kth order, and times k factorial of something with minus 1 to the k. So in that way you can actually sum it, but I didn't verify it, but I think it's working like that. And when looking on Feynman diagrams, it's where it's most useful. There's sometimes cases which you can take in sums like that very easily. If you know what is Feynman diagram, if not, never mind. That is just from QFT. Or particle course if you did. Very nice course. Okay. I'm in a record. Okay, most of the people that did that course liked it. I'm one out of 40 students that didn't like it. I don't think there were more students that didn't like it.
I don't think that.
So
you can,
wait, just let me finish. So what we will get for our sum, minus 1 to the n factorial squared. It will be, I don't know how to calculate it right now, but it will be that integral. d1, d2 divided by 1 plus d1, d2, d. Okay, that you can give to a computer and it will probably find you the solution. So that is nice. Okay, but now let's look on the question I gave you. Not question, I gave you a nice question which I made. and then we will finish. Okay. By the way, I had a nice estimation which I found on Q0 in Richardson method to the appendix of that tutorial. You can look on it. It's just a nice trick which I found. I think it's nice. It's a nice idea of using Richardson method to be correct in order of 1 over n squared. It's probably better to use Richardson interpolation, but if summing is cost you a lot, in one of the cases maybe mine is the nicer version. There are probably cases that what they did is nicer, but I'm not sure. Didn't try, so you can look on it. So let's have a look. Our problem is looking on a system which has, let's call that particles, or layers of particles that connected, I will call it with a graph. We have some layers of the graph. That is 0th layer, L0. That will be L1. That will be layer 2. Here it splits again, but now to 3. That will be layer 3. And also here. Okay? And after that it splits to 4. And then it splits to 5. And each time it gets... Okay, let's... I will not present that. Just make sure. I also made a nice graph using Python and which ChatGPT write the code, so and put that in the tutorial, so it's nice. And each layer has, if you want to think about that, for example, in a classic model, can have here positive charge Q, and here it will attract a negative charge. But maybe it will attract a negative charge with higher energy, therefore it will attract a more it will attract a much more energetic particles which will have the opposite sign, therefore the different negative sign of energy. Okay, right? And we can continue with that. The energy of each edge of, let's call that the nth layer edge, N is -1 to the n. I'm giving you that. Some characteristic interaction, energy of interaction. And it goes like something exponential because it's also interact with the things that in his level, and it's increasing each time by 1. And you have 2 particles, so in the second, and it's multiplicative. Okay, so in the second layer it will be 2 times 2, 2 to the 2. But it will be by each edge. That is just the model. And now what we ask is find the energy of the system. Okay, we know that it's a physical system. I invented, I don't know if it's a really physical system, but assume that is a real physical system. It thought should be finite. It should be well defined and finite. But what we got here, some divergence, right? But what we can do is actually writing that diverge sum, right? what it will be on starting from n equal 0 to infinity, because that graph is continuous to infinity. Each level, how many particles it has, and factorial, because the first layer has 2, then it multiplies itself by 3, the number of the n minus 1 layer multiplied by n, because each particle adds n more particles in the next layer. So summing on nth layer energy of edge, it's actually that E present edge, times the number of edges the next energy level has. We need to start from 1. It's not that matter because the 0th layer don't have any edges, and it will be pretty much 0, but 0 to the power of 0 is, mathematicians define it to be 1 for some reason, so which we will not discuss here. So I don't want mathematician here or people that did discrete math to blame. So we will start from 1. And what we will get is that divergent sum. And we want to find some feeling of what is the energy of that system, right? That can be interesting. Okay, that can be cool. I invented some system that practically looks stable because it attracts negative charges with much higher but negative energy. That thing is probably stabilizing. I don't know if it's stabilizing. I didn't look on that really rigorous and defined system that will behave like that. And you really need to explain why it behaves like that if you find a physical system. But if you find, okay, cool for you, you can publish a paper on that. Write me in the acknowledgement. At least. Okay. And well, what you get here, that is the total energy of the system. It looks stable, so it should be finite. That's why I told you that is a nice intuition problem, that when you should guess that Euler or Borel method will work if you have alternating sign, for example here alternating charge or alternating energy, so it will be stabilized. But you can extend it like Nimrod and Dima and those said for with some regularization, which I didn't mention in this tutorial, and get the sum of totally divergent series. So it also can be applied. So if you got something that not look like it's stabilized, one option, it came from the method of solving the question. Maybe doing perturbation theory in that case, like finding the root of a polynomial. You can have, if you have something like that, plus x equal 1, and you want to find all roots, two roots will diverge. Why? Because the term of x to the third want to vanish because of that delta. How it's vanishing? Go to infinity. You can do perturbation theory and look on it. You can do that as homework. You will look, hey, it's diverging. And you, in that way, if something diverges to infinity, the point diverges to infinity when delta goes to 0 and you're taking more and more terms, you can end up with something that is non-convergent, and maybe your method of solving the question were unfortunately not good, and then you need to sum things up to find what is the real solution. That can happen, but for a physical system that your method is okay, you're supposed to get something like that. Don't want to generalize it and don't catch me on the word, but it's some intuition about it. Understand? Dima?
Yeah.
Okay. So now just find it. What will be the method? Borel. But we generalize or not generalize?
Yes, you want to generalize it to k equals.
What first thing that we will do as a physicians today? We want to find it asymptotically. So how that goes like e to the n and factorial. We want, in most cases with Stirling, with Stirling you want to do the opposite. Find how n factorial is going like. But in our case we actually want to find how n to the n goes like with n factorial. So I'm taking the 0th order Stirling approximation. So it will not be exact, but you will have the feeling of what is the value of the system. I don't know how to do a Rolls bar, by the way. I think it's actually giving you upper bound, because what will be the next term? Oh no, it will be lower bound, because the next term you're supposed to have something that is n minus half, right? No. It's upper bound because the next term will be dividing by 2 pi n, I think, not multiplying. Yes. Yes, Stirling is, what is Stirling? Square root times square root of 2 pi n or dividing
I
by?
don't remember the next step.
Okay.
Every time you use only the first.
What?
Every time you use only the first. Don't remember the second.
No. Statistical, okay, you did Vienna. You did with Vienna. Safar is a nice example that if you take accurate Stirling approximation in his lecture notes in thermodynamics, you get in some cases negative energy, which indicate for a phase transition of something like that, which you mentioned, but yes, not stuff. Okay, so what we will do here is substitute that, and now it's very obvious why using generalized Stirling method will work.
That's okay.
2, yes. Actually, to the 3, I have mistake in my lecture notes. Okay, that's okay, I will not change it. Because it's pretty much the same. And I wrote the last integral with only 2 variables and not 3. But I don't care, next year's tutors will just have to correct that. And you guys that have been in the tutorial will know. Tell your friends if you want, but I'm not. I don't have to give you my tutorial notes. This year I'm giving. Okay, I'm giving every time because it can help students, but don't catch me on words there. And that is just summary of the tutorial. Like you saw, I'm not doing exactly the same as my tutorial notes, just the basic form of what happened in the tutorial. Okay, so what you're doing is just generalize Borel. Let's use that. let's write phi 3, right? Because we want that to converge. If phi 3 is not, if we will not taking
why
phi
3?
3,
Why 3?
yes.
Why 3? We have 2 there, no?
Because you want
No,
the
but
factorial
you want
with the
that
mathematics.
you want that the radius of convergence will be higher than 1, bigger than 1.
Oh,
So-
I got. So you want it. Okay.
Phi 3 of x, and it will be just e to the minus ex. Why? Because dividing that by n factorial to the 3rd power, let's do that carefully because you give me a look of I did something silly. That will cancel, and now we can just take in the n power outside, and we get the Taylor series of e to the power of e minus x. That it just can appear from our approximation. So that is also a nice way to find Taylor series and some approximation that valid asymptotically. It should be valid everywhere. Stirling is correct everywhere, approximately, very good approximation. So I'm allowed to do that. Okay, mathematicians can argue, okay, if adding zeros is not allowed, so why approximation in the divergent series is allowed? It is not, practically, but there are cases which it will work, and we can discuss on them after the tutorial. Don't want.
So now we want to use Borel series.
And now we want to use Borel series, and pretty much our solution, we can write already, substitute x to be 1, so it will be just the multiplication of UVW of the integral on I wrote here RK, need RK plus, no one corrected me. Need just the positive.
0 to
We need that to the 3rd of e to the minus u minus w minus v with phi, that is multiplication of x u v w, but our x is 1 because we just want b of 1, that will be the value of
E minus E.
that thing when we will just multiply it by gamma, and then you get the energy of the system. We'll get e to the minus e u v w d d to the, okay, let's write that explicitly. Okay, and then we got, you can plug into Mathematica if that interests you, without writing w. If w is not here, it's 0.4 approximately. But for our case, it doesn't mean anything. You can clearly see why it's converged, right? I think it's very nice presentation when it's appearing in something that's intuitive from physics. We need to balance here. So intuitively it should have a finite result for the energy, but fortunately just taking summation will not work. Maybe the representation, the model is not, you can always get your model more accurate, and that is just a toy model, and it suffers from the lack of discrete representation of that model. Okay, so you think that's it? No problem.
תודה רבה.
No problem. אז סבבה?
כן.
כן?
וואי,
ניסיתי-
איזה חום פה.
מה?
איזה
חום להתאבד.
חום למות.
ניסיתי